Good day, folks. This is tutorial number 22, and it belongs to a playlist which is called Kinematics Analysis in 3D Experiences platform. What I want to do in this tutorial is to show you how to basically write a simple rule, which means a few line of a code, so that it performs a kinematics motion, which is relatively complicated. Now, uh, now I did this problem back in tutorials, I believe 2, 3, and 4, and I'll briefly talk about it. Of course, the tutorial 2 was a block which is accelerating down a track, but that was a constant acceleration, which incidentally, constant acceleration means that the position of the block as a function of time is parabolic. Okay, velocity is linear and position is parabolic. But now in this tutorial, I want to show you how to do the motion that's described here. So as a function of time, which is the horizontal axis, the block first goes with a linear velocity, get constant velocity, which is basically 6 inch over 2 seconds. And then when it reaches that location after 2 seconds, it does a sinusoidal oscillation. And then after 4 seconds, again, it goes with the constant velocity, which is shown here. Okay. So this is not a very single expression that I can say here is the expression for the position. I mean, obviously, this has to be broken down into if t is less than 2 seconds, this is what happens. If t is between 2 and 4 seconds, sinusoidal, and if t is bigger than 4, again, it's a linear displacement. Okay. Now, in tutorial 2, I solved this thing for a constant acceleration. Remember, constant acceleration inch per second squared is going to give you a position which is just t squared. Integrate twice backward, or integrate twice the value of 2, you're going to get t squared. So I did this thing in tutorial 2. And it was defined with a simple formula. Then I did the segmented excitation, where you can put basically linear and some rather simple functions together. For example, I can take a quarter of a sine, and that's what I did in tutorial 3 by linear drop. Now, this present problem can also be done with this kind of a calculation. However, if it's not sine, then you cannot do it with segmented excitation. Uh, then I did the sketch law excitation in tutorial 4, which basically you create a sketch and you tell the software how to follow this pattern, pretending the horizontal axis is t and the vertical axis is displacement. So this was actually in tutorial number 4. What I want to do is this one. So I have to write a few lines of code, and the pseudocode that's written in here. If time is less than 2, length is velocity times time. Okay, remember the velocity here is 6 over 2 inch per second. So it's going to be 3 inch per second. So it's going to be 3 times time. If time is between 2 and 4, then the velocity is whatever it was, which was 6 inches plus a sinusoid of amplitude 6. And finally, another way, if t is bigger than 4, it's going to be another linear displacement or constant velocity. Now, first of all, notice that you do have to remember that you do have to take away these breakpoints. So don't write time here, just write time t minus 2, and don't write time over there. You have to write t minus 4. So this is something that people often forget, and we're going to do that. Now, the only thing is that this is a pseudocode. You cannot put something like that in the code that goes that you're going to have to write, because it's going to give you syntax error. So first of all, where do we do this? So if you go to the scenario, this is the scenario application, and or let me put it this way, it's a mechanical system experience application where scenarios can be created. If you look at the Tools tab over here, you see this icon. This icon is just simple rule, so you can write a few lines of code, oh, lines of code basically, and it's right there. Notice that it says if dot dot dot. So basically, it's programming. Okay. Now here is the code that I'm going to write. It's right here. The pseudocode is translated into this, and I told you that one has to be careful because you cannot write 3" underscore 3" underscore second. You have to write in a way that it won't give you syntax error. Now, if you want to see, if you wrote it and you want to see your code and change it, you have to, after you create the log citation, you click in this icon. See this right there? And this thing opens up and you can make the appropriate changes. So basically what I decided to do is run it like that. Now there are other ways of doing it too, so that's fine. Okay, this is the support of the textbook that I did 9 years ago, and it was in 2016X. Now what I'm going to do for you here is 2025X. We're going to go back and forth between these things as we go along. So let's go ahead and make it. Now I'm going to start with an assembly. Okay, there we are. So right click, insert. Let's do the base first, the track basically. This is going to be the base, and I'm going to change the name of this thing so that you can easily see what's going on. So this is going to be the track or the base, track and track, which is stationary basically. Okay, let's go make it. So on that vertical plane, I will sketch a rectangle. The width of it, I'm going to make 1 inch. The height of it doesn't matter. Even the width of it doesn't matter too, but I'm going to make it 1. And then exit. And then I'm going to pad it by, let me see now, this thing goes up to 15 inches, almost 15 inches. So I'm going to make that thing 15. Okay. Let's go here, pad it by 15. There we are. This is going to be my track. Now I'm going to insert my block, so or the box on it. Right click, insert, 3D part. I'm going to call this thing the block. Okay. Oops. Okay. There we are. Let's go make it. It's just a box. I'll make it 1 inch width. I'll make it 1 by 1. How about that? These dimensions don't matter. Okay. Exit and pad it by 1. Okay, good. All the way to the top. What we're going to do is, first of all, to fix this track. So you have to go to the assembly, and under connections, here's a fix. Click on the fix. I'm going to select the track. The track is fixed. Notice that an engineering connection has been created here. Just bear with me for a second. Right there. Okay, good. And update it. So now the next thing is a prismatic joint. So we're going to go to a prismatic. And what I'm going to do is this is a template. There are different ways of doing it. I'll do this one. Axis. Where's that? Axis. I'll do, or like this one. Axis. Look, plane, and then uh, the offset is going to be what controls the motion. Is going to be this plane to plane. So we say this is the one that I'm going to create. So axis. So this axis and that axis. This plane and that plane, or you can do the plane here, the bottom plane and the top plane of the track. Now for offset, I'm going to use what that means is that you have to control this thing. So I'm going to control the distance between these. Okay, good. All right, so that's all created. A joint has been created right there. You can see that. update. All right, I don't need any of these for now. Let me collapse them. So then I'm going to go, and because I want to do it in two steps, you don't have to. You can actually go into mechanical system experience and do it in one shot, but I'd rather do it like this. Mechanical system design. First, I create my mechanism basically. So click on the mechanism, mechanical systems design. First of all, I'm going to create my mechanism representation. It says create. Okay, good. Now, this arrow means that this box will move opposite to that. I don't like it actually, this is coming from CATIA, as you can see. In CATIA, this arrow means that the box moves in that direction, but for some reason, it's the other way around here. I'm not sure why. Okay, now if you click on the mechanism manager, you see that this is a green check mark. It's a single degree of freedom, and this is remember those two planes at the end are defined on the vertical plane. That made it a length-driven joint, so that's why this is checked. If I had not done that thing, this would not be checked, and in fact, that will not be this will not be green either. But that's okay. That's fine. Now we can check it. Here is the before we do the physics, and later on that formula in there. I click on mechanism player. Notice that this green check mark. If I move this thing to the right, that arrow would have probably told you that it goes this way, but it goes the other way. I'm not sure what they were thinking when they put that arrow in there, or I don't know what it does. Of course, you can flip it. If you flip it, oops, sorry, I have to plug in. My battery is running out. Just 1 second. Yeah, if you want, you can flip that arrow. It goes in the other direction, but it kind of defeats the purpose. I don't want it. I'll leave it like this. Okay, good. Okay, so it is working the way you anticipate. Now we're going to put the physics into it and put that law. Implement that law. So we're going to switch. We're going to switch to mechanical system experience. Now notice that I already created the mechanism by going to that mechanical systems design already created, so I don't have to do that. Say okay. All right. Now notice that the scenario has been created here. Now, first thing you want to do is to go to scenario and create a kinematic scenario, because if you don't do this, you will not have access to the kind of things that you're going to need. Okay, so I'm going to create a kinematic scenario right here, kinematic scenario, and for the parameters I'll put 10 seconds, total duration of 10 seconds, and I'll make it increments of 0.1. Okay, all right. Now the next thing I do, I need to create a law excitation. See that law excitation? Law excitation. Now, when I did this thing in tutorial 2, I had to do law excitation, and I'll show you what happens here. Let's go back there. If you do a law excitation, you select the support. The support is that command. Notice that in tutorial 2, I clicked on this f of x, and I just typed in the uh, distance or length equal to t squared, something like that. Okay, but I don't want to do it like this. I'm going to write a few lines of code. It's not a simple formula. So I say, okay, but you need that. You have to do this, because otherwise you don't have access to the things that I mentioned. Okay, so now look at where we are. We are here in the scenario. Go to the Tools tab. Go to the Tools tab. There is the Tools tab. You see this right there? And there is your simple rule. See that? Tools tab. There's a simple rule. So you click on it. Okay, rule number 1, fine. That is where you start typing your stuff. that is where you start typing this. Okay, so let's see now. Now notice that because I created these excitation, when I click on it, I mean, because I created these, the stuff that I want is already there. For example, time, etc. So I'll start writing if time, here's time. If you want to type this thing, you can do that, or you select this thing, left double click, it puts it up there. Less than 2 seconds, don't forget the S, because this is time, it has to have unit, 2S. Then this is the length. This is the length that determines the distance from the two end plates. Remember that? So you select, go to the next page, next line, and you select this, left double click, it puts it up there. Equal to, here is the speed, 3 times inch underscore. If I write 3 without the 1 here, they'll say that there's a syntax error. It cannot be used like that. If you want, you can write 3 inches divided by, well, sorry, it was, what was that? By 1 second, or let me go here for a second. Or you can go 6 inches over 2 seconds, but there are different ways of doing it. So I'm going to go and just write it the way I did it in the 3 times 1 inch underscore second. Please remember, you can write this thing as 6 in divided by 2s. Okay, so you can do it, but this is also acceptable. Times time. Time is here. Left double click. There we are. Else if here's time less than 4s, then we go to length equal to 6in plus 6in times sine of parentheses, another parentheses, time minus 2s, close the parentheses. Now I have to convert that into degrees because my angle units are in degrees. So that's why I'm going to write 360 DEG underscore s. So what I did here is basically type this stuff for you right there. And if there is a syntax error, of course, it'll tell us. Okay, good. Hopefully I didn't miss anything here. Looks fine. Otherwise, I get a syntax error. Else, finally, that means we are above 4 seconds. Your length, or all, length equal to, you start at 6 inches plus, if you go back here, you see is 8 over 6. Look at the plot. 8 units in 6 seconds. So write it the way you want. So I'll write it like that, parentheses 8 over 6. Or you don't need this parentheses, but I'll write it anyway, times 1 inch underscore s. Or if you wanted, you could represent 8 inches divided by 3 seconds, okay, times time. Don't forget the shift though, time minus 4s, that accounts for shift. Now, if you say, okay, there is any syntax error, it'll tell you, or this will give you syntax error possibly. Yeah, it says no syntax error, good. And then you say, okay, it's going to come back and says, look, when you did this excitation, created this long excitation, there was an f of x there. Remember that f of x, the writing tutorial? It says there is that thing. Would you like to deactivate that and replace this guy with it? And the answer is yes. Okay, very good. All right. So let's go ahead and to the rest of the problem scenario, and let's go ahead and compute. Compute. Very good. Let me actually change the sign. I mean, not the sign, but I can change the duration later on. I mean, not the duration, the times that makes it smaller, so it's going to go slower. But we can also animate it. We can see that. So too fast. So let's go with the smaller value. Now remember, this physics here. If you want, you can go and create a probe, and then, for example, probe meaning, for example, at this point, say, show me the acceleration of this point. As a matter of fact, let me do that. Let me close this. All right. Back to scenario. I need to make a probe here. Here's a probe. And I'm going to say, okay, show me the acceleration of this point, as a function of time. Now let's go ahead and compute. Good. If you say, show me the results here, view scenario results. Suppose I want to look at the position of that vertex that I put selected as a function of time. So I click on this view scenario results. And I'm going to say deselect everything, but show me, for example, the position of that vertex that I selected, which is X linear vertex. And then click on the plot tab, and there we are. So this was the constant velocity, then the sinusoidal, and then another constant velocity here.